So, good morning, everyone. Sorry, our apologies for the slight delay. So today it is a pleasure to introduce my friend José Alberto. I know they've been working on Quijote for at least 10 years since first light, but there was work before first light of Quijote experiment. So there was a very nice press release and a very nice data release. And today we're going to have the pleasure to listen to José Alberto showing us the results of all these years of very, very hard work. So please, José Alberto, whenever. I just remind the students in the PhD students here that they should just step down after the talk and write their names if they want their attendance to be counted. Please.
Okay, so good morning, everyone, and thanks, Carlos, for the presentation. So it's my pleasure to give you an overview of what has been the last 10 years of observations with Quijote. We started operations back in 2012, November 2012, so a little bit more than 10 years. Particularly, the past weeks have been quite exciting because we have been releasing, as Carlos mentioned, the results of the that we have obtained with the first Quijote telescope. So I will try to give you in this talk an overview of these results and give you an outlook of what will be the future of Quijote and CMB research from the Teide Observatory. So the context is observing the polarized microwave sky with the aim of understanding the cosmic microwave background. As you know, the CMB, the cosmic microwave background, is one of the pillars of modern cosmology, observational cosmology. It's a light that was produced very early in the universe, 380,000 years after the Big Bang, and it's carrying key information to understand and to set the cosmological model, which is nowadays represented by this slide, right? The summary of what we call the Big Bang model. As I said, CMB has been observational studies of the CMB have been a key tool for setting this model. Particularly here from the IEC, we have been investigating CMB for many years, starting back in the 80s with the Tenerife experiment, and then after that, several other experiments came, Cosmosomas, which was fully done here, Jodelbank IEC interferometer, Bartol, and the very small array. And Quijote is, as I will be explaining, is the next step, jumping from intensity to polarization measurements. Of course, many other experiments have been observing CMB in these years, not only from the ground, but also from space. Probably you all heard about COVID satellites, WMAP from NASA as well, that were mapping the microwave sky in 2010, and then the culmination of this was the Planck satellite of ESA. The IEC had very important participation, also other institutes in Spain. And basically, this map represents the best description that we have of the CMB anisotropies in intensity. So using this map and all the derived products from the Planck satellite, in this slide, you have the summary of what is our current understanding of the CMB, all the information that is coming from the CMB. On top, you have, we don't have a pointer, right? So on top, you can see the power spectrum of the CMB anisotropies. Okay, fine. So you can see the temperature power spectrum of CMB anisotropies, which is obtained from that map. So multiple peaks, up to 7-8 peaks that are well described by this lambda CDM cosmology with only 6 free parameters. But then there are a number of observables also in the CMB which are related to polarization. And today I will be talking a lot about CMB polarization. The E modes have been measured not only by Planck, but by other experiments to very high precision, not only what we call the E mode, but also the correlation between the temperature and the E mode. And B modes have been measured. We have measured what we call the B modes due to lensing. So the distortion of the polarization patterns that we expect on the CMB due to the fact that photons have been traveling from the surface of glass scattering to today. In addition to that, Planck was also able to measure the general gravitational potential distortion, so how the CMB is distorted when you are observing this image that and these photons are traveling through all the epoch of the universe, and all these maps, so the temperature anisotropies, the E mode, and the lensing are basically setting this standard lambda CDM model. And this list of parameters probably you have seen many times. This is basically the reference that you are all using, or the majority of people are using, or what you have in mind when you are thinking about the Planck satellite. Okay, so what is next? I mean, are we done with the CMB? So the point is that our paradigm, so the Big Bang model with a period of inflation, has been well established thanks to the observations of Planck, but there is one prediction that has not been tested yet, and this is related to the system of primordial gravitational waves that will introduce a very specific pattern in the polarization of the CMB that we call B modes. The amplitude of that pattern is unknown because we don't know what is the exact model of inflation. We don't know the energy scales of inflation. But the basic idea is that measuring the amplitude of these B modes, if we are able to detect them, we will have automatically information about the energy scales taking place in the inflationary period, so 10 to the 30 minus 33 seconds after the Big Bang. So these are energy scales which are 12 order of magnitude larger than any energy scale that we can reach with observations from the Earth, for example, from the LSC. Okay, so that's basically the goal of all the experiments that are trying to measure polarization. Probably you remember a few years ago, there was a claim that maybe we had detected this signal coming from inflation from an experiment called BICEP2 that was operating from the South Pole. Soon after this claim, the scientific community, we realized that this signal that they were detected was indeed not associated to, was not of cosmological origin, but was associated to the emission of the polarized emission of our galaxy. So at this stage, the community so realized the importance of understanding very well what are the polarization properties of all the physical mechanisms which are producing also polarization in the microwave sky. I like this slide because it's giving an overview of what is the view of the Milky Way in multiple wavelengths. Probably you are more familiar with the optical or the near-infrared images. But in this talk, we are going to discuss all this area. So what you see at the top is the radio continuum, which is basically synchrotron emission. So electrons, which are moving at relativistic speeds that are finding the magnetic field of our galaxy and are emitting. But also you have here the far infrared. And this emission is basically produced by the dust, the vibrational emission of dust particles, which again are aligned due to the presence of the galactic magnetic field. And this emission is also polarized. When you have a look to the CMB sky, so these are the results of the Planck satellites, so the 9 frequency maps. And here you can see very clearly the emission of our galaxy. So if you go to very high frequencies, 857 gigahertz, which is equivalent to 350 micron. What you see there is the bright emission of our galaxy, as I was mentioning, thermal dust emission. If you go to the very low end, you start to see synchrotron emission from our galaxy, 30 gigahertz, 1 centimeter. Okay. In between, in these intensity maps, we are lucky because we are able to see directly by eye the CMB. So the CMB is a black body, is something that is not changing in temperature. So when you look at very high galactic latitudes, I mean, all these structures that are identical in all frequency maps, this is the cosmic microwave background. Okay, so this is the view that we have in intensity. But in polarization, life is much more complicated. And these are the maps from Planck in polarization, starting again at 30 gigahertz. We are going to talk always about linear polarization. So you will see here Stokes Q and U parameters and the polarized intensity, so square root of Q squared plus U squared. So what you see here is, again, so the emission of the synchrotron at low frequencies, which is strongly polarized. And if you go to higher frequencies, 350, you see the polarization coming from thermal dust. At any frequency that you are observing there, you always see the galaxy. So the primordial signal is always subdominant at any frequency. So we have to deal with that. So in this slide, we have an overview of what we expect to be the polarization amplitude of the signal on the sky, and you see there the different processes. I was mentioning synchrotron, that is generally decreasing when you go up in frequency. I was mentioning thermal dust, that is generally increasing when you go up in frequency. And I was not mentioning spinning dust, which is also called anomalous microwave emission, which is a new physical mechanism that was discovered 25 years ago, 30 years ago, starting with the COVID data. But after that, many experiments, and in particular the experiments here at the IC, Cosmosomas, and then with QUIJOTE, have been trying to understand what is the physical mechanism that is producing this emission. Today, we still do not know if this emission is polarized or not. Okay? So what you see here is that we have a number of experiments that the satellites, WMAP and Planck, that are giving a description of the foregrounds at high frequencies. At very low frequencies, we have some surveys. Most of them are very old, but if you go very low in frequency, normally you start to have problems, particularly near the galactic center, because you start to see problems with Faraday rotation, the polarization, and so on. But what you see here is that the expected primordial signal is always subdominant at any frequencies with respect to this sky emission. Another thing that is attracting attention here is this big gap. So basically, there are no observations, I mean, in the low frequency end between 10 and 20 gigahertz, where the synchrotron emission is very bright. Okay, so this is the niche of the QUIJOTE experiment. So it's an experiment that is going to fill the gap at very low frequencies, complementing everything that has been done from space. This slide is condensing a lot of information and a lot of work of many years of research in the team. So the QUIJOTE experiment installed at the Teide Observatory consists of 2 telescopes and 3 instruments. And I want to stop a little bit in this sentence, because keep in mind that, I mean, developing a single telescope or developing a single instrument is a big enterprise. And here we are talking about the development of 2 telescopes and 3 instruments. So it's a lot of, each one of those could be a separate project by itself. The first telescope started operations, as I was mentioning, in 2012 with the MFI instrument. And after that, we started observations with the second telescope, which is doing observations at higher frequencies than 30 and 40 gigahertz. So basically, QUIJOTE in this is filling this gap that was missing. No other experiment in the world is covering these low frequencies between 10 and 20 gigahertz. So with the idea of providing a good description of the synchrotron, and also is going up to 40 gigahertz, so overlapping partially with Planck and WMAP. I mean, as I said, the development of the experiment took a lot of time. So these telescopes are especially designed to measure polarization. So they have a very particular optical configuration, which is optimized for polarization studies. Here you see the installation of the first telescope that took place in 2011, I think, in 12. So just before we started with observations of MFI. MFI is the instrument that is covering 10 to 20 gigahertz, and today I will be describing the results of this instrument. You see here the installation of the second telescope, which is basically an identical copy. Both telescopes are designed to do operations up to 200 gigahertz, but our instrumentation is ending at 40 gigahertz. And then the second telescope is equipped with receivers on 30 and 40 gigahertz, with the idea of using this information to try to reach the cosmological signal correcting the synchrotron emission using the low frequency instrument. So the QUIJOTE is a project that is led from the IC. So it's a PI-led, it's a project led from here. So I have to emphasize that. But it's also having contributions from two other institutions in Spain, Instituto de Física de Cantabria and Departamento de Ingeniería de Comunicaciones, both in Santander, and then the universities of Cambridge and Manchester. IDOM was the company that was building the two telescopes. So today I will be focusing mainly on the MFI, which is the multi-frequency instrument that has been covering this range of 10 to 20 gigahertz. This instrument is already decommissioned. So we finished observations in December 2018. And it was having 4 horns, and it was able to measure polarization thanks to what we call the polar modulators that you see here, which are basically half-wave plates that is able to rotate. So the design was done here in-house. I mean, it has been demonstrated that is having excellent performance in terms of measuring polarization. So what is the type of science that we can do with MFI? Probably the most interesting slides are the figures are the two in the bottom. So basically, QUIJOTE MFI is complementing at low frequencies anything that has been done from any other experiment. There are no other experiment in the world that is measuring at these frequencies. And moreover, at the moment, QUIJOTE is the only experiment that is taking measurements from the northern sky. So these two things are making, in some sense, QUIJOTE unique. So that is the sky, what you see on the top right is the sky that is covered by QUIJOTE. I will be talking later a little bit about this area around declination 0 that we cannot observe with QUIJOTE, which is mainly due to the emission of geostationary satellites, TV satellites that are emitting also at this frequency. So we have to correct that emission. And I will come back to this issue later. So during the 6 years that we were operating MFI, we were able to collect basically 3 years of data. So with an observing efficiency of 50%. So observing day and night, I mean, we had also some periods of, I mean, instrument modifications and so on, but in total it was more than 26,000 hours of observation. So it's a lot of data. Those observations were either focused in dedicated regions, and we already published some results about that, but probably the most interesting thing for the community, because of its legacy value, is what we call the white survey, which are observations in nominal mode, and when the telescope is spinning, basically observing the entire sky that is seen from the northern hemisphere. So this is the white survey, and is a part of what of this data release that was taking place last week. So just to give you the context, these are the science papers that we have been producing with QUIJOTE in these 10 years. The first 3 were dedicated to, obtained with dedicated observations in particular regions. And the list of papers that are coming later are the 13 associated to the white survey. The first 6 of them were already published. This is the data release from last week. And the others are going to be submitted very soon. Some of them probably tomorrow. Okay, so that's the global view. Okay, so let's go to see the maps. So this is the data release associated to the MFI. So basically you have here 4 frequency maps at 11, 13, 17, and 19 gigahertz in intensity, but most importantly in linear polarization, so Stokes, Q, and U parameters. So these maps are covering about 29,000 square degrees. They are the result of almost 10,000 hours of observations. So a bit more than 1 effective year. And they have sensitivities in polarization of the order of 35 to 40 microkelvin in 1 degree beam. So so what you see here is that when you go lower in frequency, the galaxy is brighter. So that's why you can see better the sky features in the map in the left. So if we take a closer look, what you see there is basically, okay, the southern sky is not observed from the Teide Observatory. And you see there the stripe of geostationary satellite that we have to cut because, I mean, they are emitting precisely at our frequencies. I will come back to this at the end of the talk because we are designing an experiment that will be able to observe also in this region, which is the MFI2, that will replace the MFI. So in this map, I think you will be able to identify via many of the common structures that are bright in the radio sky. So I was putting there some of them, which we have been studying in detail in the different papers. But probably the most important result from QUIJOTE is a polarimeter, is the study of the polarized emission. So this is the Stokes Q parameters map, smooth to 1 degree. And what I'm going to do now is to do the comparison with the maps of WMAP satellite. So before QUIJOTE, the best description of the synchrotron was coming from WMAP. It's a NASA mission that was observing 9 years the sky, and the lowest frequency of WMAP was 23 gigahertz. Okay, so now QUIJOTE is providing a comparable or even better description of the synchrotron. And here what I'm doing is a comparison in the same color scale, rescaling the QUIJOTE map in order to have the same amplitude for a common synchrotron signal. Okay, so this is QUIJOTE. This is the full sky from WMAP, Stokes Q parameter. So you can see that, I mean, large scale features and these emissions, which are coming from synchrotron loops, which are well known, are very well traced and characterized by the two experiments. Okay, so keep this context of, I mean, observations of QUIJOTE, basically 1 year of data, and the WMAP 9 year. This is Stokes Q, and this is Stokes U parameter. Again, you can see the comparison of the morphologies and the large-scale emission. In one slide, you have here the maps of QUIJOTE at 11, 13, and the WMAP 23. For comparison purposes, I was putting the mask on WMAP, so you can see in the same slide I mean the morphology exactly in the boundaries of the mask. Again, I insist, the maps are rescaled with a particular synchrotron spectral index of -3.1, so all the maps are having the same color scale. I don't want to transmit with this comparison the impression that is with a single frequency is enough to have a description of the synchrotron. The synchrotron is rather complicated, as I will show you in a minute, but if you go to the details of these maps, for example, if you make a zoom in this area that we call the fan region, you start appreciating different morphologies which are changing with frequency. So synchrotron.
No, de momento es así. ¿No? Claro, por eso queda grabado mientras no se cambie, porque esto debemos cambiar perfectamente. Por eso la acción es que ahora Uruguay.
Sorry. Okay. Sorry. Okay. I can go. Okay. The first paper in this series that we have been releasing last week is presenting the description of these maps. And the basic idea that I want to transmit with the next 2 slides, I'm not intending that you read all the content of these 2 slides, is that think that we stopped observations in 2018 and we are releasing now. So it took a lot of time to understand to the required level the properties of the data, to calibrate the experiment, and to do detailed comparisons with inter-comparisons and external comparisons with other data in order to control and understand the polarization properties of these maps to the required level. From this set of tests that we have been doing and are described in detail in this paper, which is 60 pages long, I would like to highlight one result, which is connected to this map that I will make bigger here for you. So this is the map as it is coming with no correction. So what you see there on top of the intensity emission is this dipole pattern, which is the CMB dipole. So it's associated to the movement of the Earth, our movement with respect to the cosmic microwave background. This was measured in the 70s and in the 80s from the ground, but it was a very difficult measurement. And then the best determinations that we have are coming from space missions. Normally, a measurement of the CMB dipole from the ground is terribly complicated because it's very difficult to have a good measurement of large angular scales from the ground. Normally, experiments are doing scans of small regions, so it is relatively easy to control the atmosphere in those small patches. But to make a measurement of this type, you have to make a map of the full sky emission. The message that I want to transmit here is that with QUIJOTE, even if it is only a 10 sigma detection, we have demonstrated that we are able to recover large angular scales. And this is telling that the stability of the atmosphere at the Teide Observatory is very good and will allow to make this type of measurements even at higher frequencies. And this is important. I think an important message because this is implying that, as you will see, other experiments are going to do observations from the Teide Observatory complementing QUIJOTE in the future. Okay, so now I will go to talk a little bit about the synchrotron emission. So I was mentioning at the beginning in the introduction that when you observe the polarized skies, you have basically two types of emissions, synchrotron at very low frequencies and dust, thermal dust at very high frequencies. When you look to the morphology of that emission, what you see there is the reconstruction of the synchrotron from the WMAP satellite, from Planck satellite at 30 gigahertz and the reconstruction of the dust at 350. You see that these patterns that you see at large scales, which are basically tracing the direction of the magnetic field, which is at 90 degrees with respect to the direction of the polarization, are very similar. And the reason, I mean, when you compare the synchrotron and the dust, and the reason of this correlation between the dust and the synchrotron is that there's the same physical mechanism, it's the same galactic magnetic field that is orienting the dust grains, is the same one that is telling the cosmic rays how they are moving and then how they are emitting. So you expect that correlation. So it's important not only to understand dust and synchrotron separately, but also understand the correlation of the two processes. Okay, so the best description that we had of the synchrotron until now was given by this map of the Planck satellite, but now with QUIJOTE we are able to reconstruct in the northern sky this synchrotron emission, which is basically everything that we see in the 11 gigahertz maps. So what you see there on the left is our reconstruction in color scale, is the polarized intensity. And again, the patterns are the reconstruction of the galactic magnetic field, which is basically at 90 degrees with respect to the linear direction of the linear polarization. This is another projection of the same map, looking only to the northern sky. Another important result that we have obtained in this data release is, I mean, not only an image of the synchrotron, but also the description of how the synchrotron is changing with frequency. This map that you see there on the top right is the first map that is done of the spectral index of the polarized synchrotron emission in the northern sky. So this map comes from the combination of Planck, WMAP, and QUIJOTE. Okay, so when we talk about the polarized spectral index of the emission, I'm talking about, I mean, we are assuming that the emission is given by a certain power law, and we are describing the exponent of this power law. Okay, so what we have found with this map, the first thing that is attracting your attention is the granularity. There is a lot of structure there. Okay, so if you make a histogram of the values of that map, we find an average value of minus 3.1 that I was using before in the rescaling of the maps, and you see a dispersion of 0.13 in that value, which in this histogram is represented as the red histogram. The message here is that the existing models of the synchrotron, which are represented by this histogram of blue lines, we are having incorrect values of the average synchrotron emission in polarization, and we are underestimating the actual distribution of the synchrotron. So in one sentence, synchrotron is much more complicated than expected. It's varying more. And QUIJOTE has contributed to establishing this good description that we have now of the synchrotron. The second thing that I think is important is the description of the B modes. I've been talking all the time about measuring primordial B modes. Okay, so from our map, we can reconstruct the B modes of the galaxy due to the synchrotron. So these are the maps of the E and B modes from QUIJOTE. And in particular, look at this map. In principle, it seems that this has a little less structure than the E mode, and this is very good. So we have shown with QUIJOTE that there is approximately a factor of 4 less power in the E mode than the B mode, and this is a new result. So this is important because maybe B modes are not as important as expected, but still, we need to measure them in detail and then take this map as a reference to correct any future measurement of the primordial signal. So for example, if we take this map and we take the spectral information of how synchrotron is changing with frequency, we can predict how any future experiment measuring at 90 gigahertz, 150 will be contaminated by this synchrotron emission. Okay, so the message here is that these maps that we are releasing are a key tool for any experiment doing observations from the northern sky in the future. Apart from these results, in the release, we have been including some additional papers, and 2 of them are related to the description of the anomalous microwave emission that I was mentioning at the beginning. We already presented in a paper in 2017, led by Ricardo, the best upper limits on the polarization of this emission. I was mentioning that this is a new mechanism, which is basically described in this slide. So it's a new physical mechanism that is emitting around 20 gigahertz, precisely at the QUIJOTE frequencies, and is probably associated to rotational emission of the dust grains. But we still do not know if this emission is polarized or not. The physical models predicting several degrees of polarization, but we need to confirm with an experiment, at which level this emission is polarized. So the best upper limits that exists at the moment are coming from QUIJOTE at the level of 0.2%. And in 2 of the papers in this release, we have been basically studying over almost 60 regions and characterizing the physical properties of this emission. The summary of the result, probably the most important result, is that we are showing that, again, the models that we're using in the literature to describe this anomalous microwave emission are not properly describing some of the key parameters, as the width of this distribution, the width of this emission, or even the peak frequencies. Okay, so this information that we are providing with QUIJOTE will be an important feedback to these models in order to improve the description. Another paper in this series is related with the study of the Galactic Center and the so-called the CMB haze. The haze is an emission that was discovered in WMAP data and later confirmed by Planck, which is an emission that you see there in red color in this map on the top right, and is correlated with this blue emission which are coming from the Fermi satellite, the Fermi bubbles. If this correlation is real, studying this region in the galactic center is interesting because this could give us hints on, for example, dark matter annihilation in the center. Okay, so with QUIJOTE, we have in this series we have a paper in which we confirm the detection of the haze. So it was WMAP and Planck that was measuring this. We have measured again with QUIJOTE, so we confirm the existence. And we have obtained hints on the polarization of this emission that might be useful to separate the nature of this emission, pointing probably towards different synchrotron emission than the average that we have in the galaxy. But again, providing key information to properly model the origin of this haze emission. And then there is another paper in which we are doing a systematic study of more than almost 800 sources, radio sources. All of them were already known, but we are providing information at these new frequencies. This catalog is useful. I mean, the data could be used also for doing variability studies. But the basic message is that if you use our QUIJOTE data and to compare with evolutionary studies of the population of the sources, basically our results are consistent with these evolutionary studies. Okay, so I try to give you the highlight of the 6 papers that we have released, but there are more results to come, and I'm sure that will be new seminars. So I mentioned these 7 papers that are in preparation, plus the one describing the data processing pipeline. So probably during this year, there will be other seminars describing these new results to come. Okay, so where we are now with QUIJOTE. So I was speaking all the time about the first telescope, but the second telescope is already taking observations. We had the first light in May 2016 with detectors at 30 gigahertz in this instrument that we call TGI. And then in 2018, 2019, we were adding also detectors of 40 gigahertz, which are basically of the same physical size, so they can be exchanged in the same cryostat. The observations with this instrument, had some difficulties because we had issues with the vacuum in the cryostat of the TFGI. Because also of the pandemic, the observations were stopped during some period, but they have been recently started. At the moment, we are not observing because we are going to do an upgrade of the instrument to include new receivers. But we have already started accumulating data. So here I have a few slides basically saying that the sensitivities of the instrument are expected in terms of noise properties and the beam response. So this will be an instrument providing of the order of 20 arc-minute resolution at both frequencies. And the preliminary maps that we are obtaining in different regions are, very promising. So these results are part of the thesis of Matteo. So as I say, very promising with the expected sensitivities that we had for this instrument. So what is going on with the first telescope? MFI was decommissioned in 2018. So the feedback that we have been, because this data from QUIJOTE MFI, we have been presenting this data, or the status of the data in many years, in many conferences during the past years. So the feedback that we have from the community is that having a good description of the synchrotron in this frequency range that is covered by MFI is an extremely important ingredient for doing a proper study of cosmological beam modes. So QUIJOTE is filling a niche that, as I said at the beginning, is not covered by any other experiment. Because of that reason, we decided to go ahead with this idea of MFI2, which is an upgrade of the MFI. That is going to be basically a factor of 3 more sensitive. But probably the most important thing is that it's going to use a full digital backend based on FPGAs that will allow us to remove the contamination from geostationary satellites and any other emitting satellites, Starlink and other satellite constellations that are emitting in the radio frequencies. The idea is that basically we are going to scan in frequency now all the emission and in the full band between 10 and 20 gigahertz. So we will be able to identify at which subbands we have emission from the satellite, and we will be cutting that emission. So that will allow us to do observations even in that region where we have the geostationary satellites, basically cutting the frequency bands when we have the emission from the satellites. In the past, with MFI, it was not possible because MFI was a very broadband instrument. Okay? So basically, still we are keeping the same broadband, but inside the band, we are identifying where we have the interference and we cut that. So that's the basic idea. The instrument is basically integrated, and we are doing the tests now, which are going extremely well. And hopefully by spring this year, the instrument will be moved to the Teide Observatory. So we will start with the commissioning. Okay, so what is the context of the CMB research in the coming years? So I was speaking about QUIJOTE, but at the Teide Observatory, what we call the CMB lab is not only QUIJOTE. Thanks to the QUIJOTE results and thanks to the excellent performance of the atmosphere here at the observatories, other experiments are joining and complementing QUIJOTE in this idea of measuring primordial B modes. Groundbear is an experiment that was installed in 2019 that is giving information at 150 and 220 gigahertz. It's already in operations. And at the end of this year, probably beginning of the following, we will have LSPE strip that will be observing at 43 and 90 gigahertz. So altogether, these three experiments are providing information between 10 and 220, so 10 frequency bands, and they constitute the only experiment, the only observatory doing CMB observations from the northern hemisphere at the moment. And particularly, this niche of QUIJOTE is unique also in the world. There's another experiment on that. Apart from these experiments, we will have in the future also a spectrometer, but I will talk probably another day about CMB spectral distortions. It's a totally different topic. So what is the outlook for the future? So the idea is that after Planck, Europe it will be involved in this LIGHTBEAR mission, which is a proposal led by JAXA, the Japanese agency, that is expected to be launched at the end of this decade. So LIGHTBEAR will be observing during 3 years in 15 frequency bands, starting around 34 gigahertz, with the aim of targeting tensor to scalar ratio at the levels of 10 to minus 3. So basically, improving by a factor of 10 at least what has been done or it will be done from the ground in the coming years. We as IC, we are also involved in this project. Ricardo is the local PI, but I mean, the CMB group is also participating. And the context here is that all this information that we are providing with QUIJOTE is still useful for any future experiment, and in particular LIGHTBEAR. So doing these low frequency observations, 10 to 20 from space is very expensive because, I mean, these are big detectors, big horns. So, I mean, it's expensive to put in the payload of the satellites, such a big receiver. So the information that we are giving will be useful in any case for any future experiment, and in particular LIGHTBEAR, to do the correction of the synchrotron. You have to do it anyway. So remember, always the mission of the galaxy is dominant over the expected cosmological signal. Okay, so this is the summary of this research of 10 years with QUIJOTE and the outlook to the future. So with MFI, we were observing 6 years. Probably the most important result is this map. This set of maps of more than half of the sky, 10,000 hours of observations, 4 maps at 11, 13, 17, and 18 gigahertz. Which will be a key ingredient for cosmological studies for ourselves, for understanding the synchrotron and correcting that at 30 and 40 gigahertz, but also for any future experiment, and in particular LIGHTBEAR. Probably the most important results of this release is that we have set the basic properties of the polarized synchrotron, showing that the synchrotron is much more complicated than expected. There is a spatial variability of the synchrotron spectral index. There are hints of curvature, and I was not speaking about that. There is another paper in the series about that, but we are starting to measure the correlation between dust and synchrotron. You have to take into account also that correlation if you want to properly correct both emissions. If you're not taking into account that, probably you are overcorrecting when you are subtracting. And regarding the anomalous microwave emission, basically we have set the best upper limits that we have nowadays on the nature of this emission. We still don't have a detection, but if the emission is polarized, we hope that we should be able to measure that with the TGI and FGI. So the observations for the coming year, so continuing observations in the second telescope with TGI and FGI, with the aim of completing galactic observations and cosmological regions in a survey of 3 effective years. MFI2 will come hopefully at some point during this year. And the results of Quixote will be combined with other experiments at the Teide Observatory, Groundbird, and Strip. And all this with the perspective of, in the future, in the next decade, doing the scientific exploitation of LightBear, but taking advantage of all the things that we have learned from Quixote. Okay, so this is my last slide. This was an effort of many years, so we have to acknowledge all the support that we have here in the Institute, at the IC, at the different divisions, research, instrumentation, the workshops. I mean, we were leading the construction of this project. I mean, it was essential to have all that support. We have to thank the staff of the Teide Observatory, TOTS, MOD, maintenance, because without them, it will be impossible to do the operations and the commissioning. And I have to list there all the projects that that have been supporting Quixote with during all these years. You see many of the national program, but also you identify there a Consolider Ingenio program and an European program, radio programs that was also supporting Quixote. So from our Quixote team, thank you all. I'm happy to take questions.
So thank you, Jose, for this very, very nice summary. So we start taking questions from the audience, from the people here in the aula. So please.
First of all, congratulations to everyone involved in this very nice project. I have a couple of questions. So is it possible to make already some measurements of this R parameter involved in well, primordial gravitational waves and also inflation using correcting the dust emission with this data?
So this data is modeling the synchrotron emission.
Yes.
Okay? So the best limits that we have nowadays are at the level of 0.03, right? This is coming from the latest result from BICEP. The BICEP observations are from the south, okay? So the ideal thing will be to have a similar or equivalent thing to Quixote in the southern hemisphere, and we are exploring that. But let me say, the important message is that if you are aiming to reach values of 10 to the -3 in R, then you have to correct both synchrotron and dust. This is the important message.
So there is no overlapping region, because I see you see.
So we are reaching some parts of the southern sky, but we are not overlapping with the BICEP patch.
Then have you tried to measure the peculiar motion of the local group with the dipole?
So the measurement that we have of the CMB dipole is, as I said, is a weak marginal detection. So the best detection that we have is the one coming from the Planck satellite. So this is, in our case, is used as a consistency check to see that we are able to recover properly large angular scales. But we don't make any measurements. Maybe indeed Carlos can speak about this in individual objects, but I mean, this is a global measurement, okay?
I see. And my last question would be, can you learn something about the history of the Milky Way with this data?
Yes, I mean, so if you model the synchrotron, so the natural thing that you can do is a reconstruction of the galactic magnetic field. For that, you need to input information of the distribution of cosmic rays, so relativistic electrons. So the Planck satellite attempted to do some modeling of the synchrotron, having as an input some information from simulations, because using Planck data alone, it was not possible to fix the spectral index of the synchrotron. Now with QUIJOTE, for the first time, we are able to do that. So that is opening the possibility of testing models of the distribution of cosmic rays. So this is one of the things that we are planning to do, yes.
Well, thanks a lot for the nice seminar and congratulations again for these super nice results. I wanted to ask whether it is either possible to use directly these foreground maps or to get inspiration from this kind of project and results to also use, to use this foreground detection techniques also for other projects like SKA, because I know that, for instance, in the case of SKA, people are massively using previous results from the CMB experiments.
Yep. So the answer is yes. I mean, indeed, the tools and methodologies that we are using for doing component separation in this type of experiments, some of them can be easily adapted. I mean, not easily, but I mean, they require some work, but can be translated or adapted to SKA. Indeed, I mean, here at the Institute, there are several people, including myself, that are joining the different working groups in SKA, and in particular, the component separation group. So yes, I mean, think that when you go down in frequency, synchrotron is becoming brighter and brighter. So, I mean, having the reference of large angular scales coming from QUIJOTE are useful. SKA is partially overlapping with MFI because it's going up to 15 gigahertz. So yes, I mean, there are natural synergies between what we are doing and what SKA will be doing.
Thanks for the talk. I have a question about how do you correct the sky? How big is the sky?
In polarization?
Yes.
Okay, so maybe I can go directly to the physical models. I mean, there are different families of, it could be done here. So there are different families of methods that are doing the component separation. For example, in QUIJOTE, what we have been doing is using a subset of those models, which are called parametric models. So basically, we do a parametric description of how the galactic emission is changing with frequency. So in particular, the synchrotron is assumed to vary as a power law with some spectral index. Thermal dust is usually modeled with a modified black body or modifications of that. However, the CMB is a black body, so we know very well the spectral dependence. So the idea is that you combine all the different frequency maps in order to extract a signal that is having a black body spectrum. Okay, and if you have a parametric model, as we are doing, then you can extract also the parameters describing the different components. So doing that, we are able to reconstruct the synchrotron amplitude, and in particular, this, what you see there up right, which is one of the parameters, which is the spectral index map.
Sorry, my question is related to the sky background. So the sky in the atmosphere.
Okay. So based on the MFI data, we can say that the emission of the atmosphere is basically unpolarized. So there is no need to do any correction in polarization. In intensity, the atmosphere is having a temperature. So when we observe at different elevations, we see this change because we have different air masses. Okay, so in order to correct for the atmosphere in the intensity maps, only in the intensity maps, we are building templates of the atmospheric emission every 2 hours based on a large-scale modes. So basically, the instrument is scanning big circles of more than 60 degrees on the sky continuously, and accumulating 2 hours of data, we build templates of the sky emission at large angular scales,
So
and we correct that using the information of how the atmosphere is changing with frequency. So this is these maps that you see here are the projections of the residual component of atmospheric emissions that we have to subtract from the final maps. Sorry, I misunderstood the question.
Any other questions from the aula? If not, I'd like to ask my own question before this one question in the online too. First, this one. You have focused on the spectral index of synchrotron from the polarization point of view, because it has relevance for the measurement of the modes which contain this cosmological information. What about for intensity? Have you checked whether the spectral index and its variance, each spatial variation, is the same for intensity as for polarization?
Okay, so this is a very interesting point, and this is connected to some of the papers that are pending. So the next one that is going to probably be submitted very shortly is the one that Mateo is leading, where in intensity, he's doing a component separation in the galactic plane. Okay, again, here for the first time, we are we are studying the spatial variations of the synchrotron spectral index. Okay, because in the previous analysis that was done by the Planck satellite, I mean, they were basically fixing for the spectral index. Okay, so now we are able to measure this, and then there will be another paper that is in preparation with the component separation in intensity. The intensity modeling is much more complicated because in polarization you only have the synchrotron and low frequencies. In intensity you have anomalous microwave emission, synchrotron, free, and then the physics of the synchrotron is also complicated because in polarization basically you only have contributions to the synchrotron coming from those regions in the galaxy where the magnetic field is regularly oriented. However, if you have turbulent layers, those layers are contributing to intensity, but not to the polarization. So in principle, you might expect some differences, but this is one of the things that we are starting to do. The first comparisons that we have done in particular regions are showing that the spectral index in supernova remnants, for example, are reasonably consistent between intensity and polarization. But a detailed study in the full sky is still pending, and is one of the things that we are doing.
And a quick bit about the haze. You say you have detected the haze in polarization.
Yes.
It had been detected in intensity. So is it looking the same? Like this, is an obvious similarity between?
So in intensity is looking the same as the detections of WMAP and Planck, and in polarization, when we subtract all the other components, we see a residual. Okay, so this residual could be either ascribed to the haze or could be ascribed to probably an incorrect modeling of the synchrotron. And this could be due to the fact that, for example, if you are having curvature in the synchrotron, different dependence with frequency, then you will see the residual.
It should be coherent, right? Because what you see is that the synchrotron spectral index changes like very randomly from place to place, whereas the haze, you would have to have a uniform change in the spectral index.
Well, you see here the residual excess in the maps in polarization. So at the moment, I mean, we cannot say easily if this is due to changes in the curvature of the spectral index of the synchrotron, or it is actually ascribed to the haze. So we need to do physical modeling of this emission in order to test for this. But this is the observational result. There is an excess of emission.
Okay, let me give a word to the people online. So I think that first it was, you see, I think it was Julio first asking. Julio Castro, do you mind asking your question?
Hello. Hello, everybody. Thank you very much. Can you hear me?
Yes.
Yes. Okay. So thank you very much for the interesting talk. And I have two questions I would like to do. You have been explaining a lot about the stability of the atmosphere we have in the observatories, and I would like to, if you could elaborate a bit more in terms of water vapor, because we have, in fact, we have strong stability in terms of in the periods with very low water vapor content in the atmosphere. And I think that you have explained a bit before. I suppose that it is important, more important in the intensity maps than in the polarization maps. But I would like if you can explain a bit more about this. And the second question is if you can explain a bit of QUIJOTE as a visiting platform for instruments, for example, the presence of keys instruments. And I don't know if you have in plans of other visiting instruments that are coming to use QUIJOTE as a platform for testing or so on. Thank you.
Okay, thank you. So the first question is related to measurements of the PWV. So yes, well, as you know very well, I mean, QUIJOTE can be used as an instrument to measure, to have an instantaneous measurement of the PWV content, because any change, I mean, when we move the telescope in elevation, changes in the temperature can be directly translated into values of PWV. So this is a work that is led by Ricardo here at the IC. You know, but I mean, I can say that the PWV measurements have been correlated with the GPS measurements that we have at the observatories, and they have excellent agreement. So these are independent ways of testing the PWV. Regarding the impact of the PWV in our maps, one of the multiple tests that we have been doing are enclosed in the category that we call null test. Basically, we split the data in different parts. And one of the different splits that we have is doing a map of data in high PWV conditions and data in low PWV conditions, and then compute the difference of those maps. If we are properly correcting from everything, we shouldn't see residuals, and this is the case. So, I mean, in terms of PWV residuals, we are confident. But if you are asking about the possibility of measuring, yes, basically we have a record of many years of PWV measurements that can be extracted indirectly from the data. So that, I hope that answers the first question. And the second question is related to the usage of QUIJOTE for other instruments. And indeed, you were mentioning, I think, keys, right, Julio? Yes. So keys was a visitor instrument that was installed. So after the decommissioning of the MFI in 2018, in 2019, we had this visitor instrument from the University of Grenoble with the idea of doing a spectroscopy of different regions, and in particularly the ultimate goal was galaxy clusters in the frequency range between 100 and 200 gigahertz. Okay, so the instrument was a prototype of an instrument that France was developing for the Apex telescope in Atacama. That is called Concerto, and indeed is operating now. So basically, with these observations, so we were able to learn about how to do this type of spectroscopy. So the team was learning about the performance and how to do the data processing and so on. And there was well, at least a couple of publications related to that. So yes, in principle, I mean, there is the possibility of using this telescope with other instrumentation once we finish with the observations that we are doing with these instruments.
Thank you. So last question for Almudena.
Yeah, hello, good morning. You hear me?
Yes.
Okay, very impressive work. I have a question that just to clarify myself. You map the polarization across the sky, you associated, after you correct for contributed sources of polarization to the microwave background, and in turn you associated as well with the origin of the universe, okay, cosmic origin. So if you see polarization as associated to the universe or cosmic origin, and we understand what polarization is produced by non-thermal emission, synchrotron emission of dust, are you implying that the cosmic origin we have already dust or non-thermal sources in place?
So I'm not sure if I'm getting the point. So the basic idea is that we can separate those signals which are from galactic origin due to the frequency dependence. So the fact that if you find some particular pattern in B modes that is scaling in frequency exactly as you expect for the thermal dust, then you know that this is coming from the galaxy. And if you have something that is a black body, and then you know that is primordial in origin. So I don't know if you are.
I understand that, but you were saying that the polarization somehow map the microwave background. I understand.
So in the case of Planck, yes, you decontaminate for that, and then you are able to detect. I was mentioning the E modes in the talk, and from there you can measure the properties of the microwave background. These measurements are cosmological in origin. Indeed, one of the very nice exercises that can be done with the Planck data is the fact that once you fit for the intensity data, so you have the lambda CDM model with the 6-parameter fix. Then once you have that model, you can predict that there is 0 free parameters. You can predict what is the level of the E mode, okay? And the data points of the measurements of Planck of the E mode that totally agree with that prediction. There are no free parameters there. Okay. So yes, so using this methodology, we have separated the E mode, which is of cosmological origin. When we try to do that for the B mode, all the bottom line is that all the signals that we have found are changing with frequency. So all the B modes that we have measured are from galactic origin.
But these E or B modes are polarization signal. Is
yes.
that?
Yes.
So that is my point. What is causing this polarization signal at cosmic origin? Because you are talking about polarization.
So the cosmological origin. Okay.
That's the point. I mean, it
okay.
is residual at cosmological origin.
Okay. So
are you implying that there are non-thermal sources?
No. So the CMB is Thomson scattering. So a Thomson scattering electron by electron, a photon by photon is linearly polarized. So what you see is this prediction of having E modes is a clean prediction of the physics of the CMB, which is Thomson scattering. There are no non-thermal sources.
Okay.
Cosmological origin. However, I have to say that one of the things that we are investigating with the Planck data, and we will do with LightBear in the future, is search for primordial B modes. Sorry, primordial magnetic fields that we know, thanks to Planck, that they are subdominant with respect to the usual anisotropies. So we, in comoving scales, we know that nowadays a primordial magnetic field should be smaller or of the order of 1 nanogauss. And this is something that we can investigate. But now I understand your question. So the physics of the CMB and the E modes and B modes is Thomson scattering. So there is no non-thermal physics.
Okay, I think we have to wrap up here. Before we thank José Alberto again, let me first remind the PhD students they have to sign up here, and that there is a scientific coffee at the cafeteria right after this meeting, right? So Thank you.